All right, section 1.4, we're talking about functions today. So, a definition of a function is, when it's a relationship is what we're talking about. All right, so a function is the relationship between any two sets, A and B. All right, the set A, all the things that are in A, which are usually numbers, but sometimes other things, that's the domain. All right, that's also our input and our independent, right? And then B has our range, which is our outputs, and that's our dependent. So here visually we can take a look. All right, A is the domain. Inputs are 1, 2, 3, 4, 5, and 6. And they're going to match up with our answers, our outputs, which is the range. Typically in algebra, this is our X, and this is our Y. And let me write this in also. X is going to be our independent, because we're choosing. Right? We're choosing what time of day, maybe 4 o'clock we do something, or we check the clock, and Y is dependent because we have to wait for what we pick before we can spit out an answer of 15. All right? So we can take a look here, a couple rules. Every element in A has to have a match. So you'll notice here 1, 2, 4, 3, 5, 6. Every one goes and matches up with something. It's okay to have answers output that doesn't match up with anything. So 6, 14, all the rest of them. That's fine. 2 or more elements in A may be matched with the same element in B. We're noticing that here at 3 and 4 o'clock we get 15 degrees Celsius. But we can't go the other way. You notice that none of these we can't say at 5 o'clock it's 12 degrees and 10 degrees. If we did that, we would not have a proper function. Wouldn't have one-to-one output. All right? So for every input, there is a matching output. Okay? All right. 4 ways to represent a function. Verbally, we can write a sentence. Numerically, that's our T table, right? X and Y. It's numerically. Graphically, we can graph it with a set of points, which we've done so far with our scatter plot, right? Or algebraically with a relationship y equals 5x, something like that. All right, so 4 different ways that we can do it. And usually one is the problem, right, in the math book, and the way we would solve it is one of the next 3 ways, numerically, graphically, or algebraically. All right, so let's do a couple examples here. Example 1, determine whether the relationship represents y as a function of x, whether this fits the rules. All right, A, the input value x is the number of representatives from a state, and the output value y is the number of senators. All right, is this a function? All right, so x is reps, and output is senators. All right, so we have how many senators in every single state? There's always 2. All right, and so how many representatives are there? Well, there's different from each state. Maybe there's only 2, but maybe there's 10, or maybe there's 40. Right? You can have a lot of them. They're all pointing to 2. Is that allowed? Yes, it is. Every input can have the same output. If this was flipped and 2 was pointing to 3 different outputs, this would not work. All right? So we can see that right away on example B. 2 has 2 separate outputs. Immediately, no go. That is not a function. All right? And then C, graphically, we can check, does this pass? Well, this is the vertical line test. Right? Does this ever touch 2 points at the same time? No, it does not, so this passes. So yes, this is a function that is allowed. All right, so a couple different ways we can look at it. See if you can figure out the answer to exercise 11. All right, quickly I want to come back to the independent and dependent variables. That's very important. Typically, x is your independent and y is your dependent, all right? But it's the result that matters. The dependent one is the result, right? And the independent one is the one you get to choose. Right, so that comes up in a lot of different places, independent versus dependent, and let's just make sure that we're clear on the difference. All right, so example 2, which of the equations represents y as a function of x? Well, the easiest way to do this is move this over so that y is by itself. So y equals 1 minus x squared. All right, on this one, I could have -5, square it, and I would get the same answer as 5 and squaring it. But since x is my input, no matter what happens, if I have a different input, 5 or -5, right, I can only get one answer. Y equals whatever the answer is. So that's allowed. We could check this graphically also. 1 minus x squared is a parabola that looks like that. And that does pass the vertical line test. If we look at this other one, y squared equals 1 plus x. Okay? On this one, if I choose, let's choose, I don't know, 8 for x to make it easy on ourselves. Y equals 1 plus 8. So y squared equals 9. And so y equals either 3 or -3. Look what just happened. If I chose 8 for x, I either got -3 or +3 for y. So that is not a function. All right, and if you were to plug this in graphically, it'd be a little tricky on your calculator, because remember the calculator is only going to graph the positive version of this unless you explicitly tell it on y1 and y2 to do the two different versions. The square root of 1 plus x and also the negative square root of 1 plus x. So be careful doing this graphically, but if you do it right, you should end up with something that looks like that. Definitely does not pass the vertical line test. You're up with exercise 21. All right, so function notation, this is the f of x notation, and all we're doing here is replacing y with f of x. All right, and just visually this is really nice, because what we can do here is say, instead of y if x is something, we can keep track of our x's right here. What's the y value if x is -1? What's the y value if x is 0? What's the y value if x is 2? All right, so f of x, exact same thing as saying y. Let's plug some in here. Let's find g of 2 if g of x is -x squared plus 4x plus 1. All right, so everywhere we see x, we're going to pop in a 2. So -2 squared is -4 plus 8 plus 1. -4 plus 9 is 5 for a. How about t? Everywhere I see an x, I'm going to pop in t. Negative t squared plus 4t plus 1. And so that just turns into -t squared plus 4t plus 1. Notice this stays negative because the squared is only going to the parentheses, negative out front. And the last one here gets a little trickier on c. So we've got negative x plus 2 squared plus 4 x plus 2 plus 1. So notice this is in our parentheses. That's what we're plugging in everywhere we see x. So we're going to have to FOIL this first. Negative x squared plus 4x plus 4 plus 4x plus 8 plus 1. Let's clean this up. Negative x squared minus 4x minus 4 plus 4x plus 9. X's cancel, and you've got negative x squared plus 5 as a result. So plugging in 4x. Try it on exercise 41. Move this out of the way for you. 41. All right, so piecewise. Piecewise is something where we're going to have two graphs represented on the same coordinate plane. All right? So here's what we've got. I'm going to, for a moment, pretend that this is not here. Not even here. and I'm going to graph x squared plus 1. Well, that's a parabola that starts at 1 and goes like that. Okay? However, I only care about this graph is if x is less than 0. Okay? So I need to get rid of the part of the graph where x is bigger than 0, to the right. All right, let's bring this back in and say, what's the other graph? Well, the other graph says x minus 1. All right, so I got to go down 1. And then it's up 1 over 1 with a slope of 1. I only care about it to the right of 0. So I'm going to go just this side. I'm not going to have anything over here, right? Because that's to the left of 0. That's where x is less than 0. And the last important thing, I need to put a circle here, and it's a closed circle here because of the equal to part of this graph. I'm going to go ahead and show you how to do this on the graphing calculator as well. Let me bring that up. And it's just putting two equations in here. So let's get our y equals here. I'm going to clear this out. All right, so the first part here says x squared plus 1. I'm going to put that inside of parentheses, x squared plus 1. And then on the same line, parentheses, x is less than 0. X, second math, which is this test right here. And I go for the less than, number 5. X is less than 0. Close my parentheses. Line 2, in parentheses again, x minus 1. Parentheses for the restraint, x is greater than or equal to, which is number 4, 0. I'm going to go ahead and graph this. I'm going to make my window negative 10 to 10. And I'm just going to go ahead and do that for the y's as well. And let's see what happens. Okay, we have two different graphs going on right there. Just so it's nicer to see, I'm going to go ahead and do a zoom fit, which is 0. And that'll redraw it here. And then it's popping back up. Since we know it's negative 1, I might want to change my window here, just my scale, negative 2 to, I don't know, 20, something like that, just so I can get a better view of it. There we go. And from negative 1 spinning back up. So two different graphs, but we only graph part of each one. All right? So see if you can do that for exercise 49. All right, example 5, finding values for which f of x equals 0. That's the same as saying y equals 0. All right, so we're going to solve this. Let's do a first. F of x equals 0, so we replace f of x with 0. Negative 2x.
Hey.
Hey.
I think I left my bag here.
Sorry about that. Miss Barber just came in. She left her bag in the classroom. All right, let's keep going. Here we go. Negative 2x plus 10. We're just going to solve this. Negative 10 equals 2x. Negative 2x divided by negative 2. And x is 5. All right, and so that's also an intercept, 5, 0. Because we said that y, or f of x, is 0. Let's do the same thing on b. Fairly straightforward. 0 equals x squared minus 5x plus 6. This is a trinomial. We need to factor it. Since this is a positive and this is a negative, we're going to have two negatives. One's 3 and one's 2. We multiply to 6. We subtract to, or we add to negative 5. All right, so to solve this, x is 3 or 2. If we were doing intercepts, we would have two of them, 3, 0, 2, 0. All right, solve for your zeros, and I'm sorry, that's one thing. This is what we say when we're solving for the zeros of something. So see if you can find the zeros on exercise 59. All right, example 6. Find the values of x for which f of x equals g of x. All right, so this equals this. Well, let's go ahead and substitute in. F of x equals x squared plus 1. That's equal to 3x minus x squared. Let's go ahead and solve. We'll add x squared to both sides. Okay, so we've got 2x squared. We're going to minus 3x. Get minus 3x plus 1. We put everything on one side. We get 0. All right, another trinomial we need to factor. It's going to be 2x and x. The only way to multiply to 1 is 1 and 1. And since we're multiplying to a positive, but then we're subtracting, they must both be negatives. And that does work out. That equals 0. And so let's go ahead and solve this. X equals 1/2. X equals 1 on this one. Okay? And we are going to check to make sure that these answers work, but since there's no denominators up here, we're okay. All right? Make sure that you don't have any extraneous solutions. Let's check B. X squared minus 1 equals negative x squared plus x plus 2. We'll bring the x squared over and get 2x squared. Let's bring the x over and get negative x. And let's subtract 2. And so we'll say negative 3 equals 0. And so let's factor this. 2x and x. And we've got 3 and 1 are our only choices. The right spots need to be here and here so that we get 3 and 2, so we can subtract to 1. We want the negative 1 to be bigger, so that means the minus goes here and the plus goes here, which means that x equals 3/2 or x equals negative 1. Those are our solutions. All right, when you're ready, exercise 67 is all yours. All right, let's talk about the domain. The domain of a function is going to be all of the x's that I can plug in. All right, domain is all the x's, x values I could choose to plug in. If I can plug in anything I want, then you're going to say the domain is the set of all real numbers. Right? All right. Sometimes you can't get all the real numbers because if you divide by 0, like here, if x equals 2 or negative 2, that's going to mean you're dividing by 0. So in this case, we would say the domain is all real numbers except x cannot equal plus or minus 2. We also cannot divide by a negative, or I'm sorry, square root a negative. Cannot have a negative number under here. So we know here the domain, x has to be greater than or equal to 0. Okay? All right, so let's try to find the domains of these functions. Find the domain of each function. In this problem A, it's all the x values. Here they are. So the domain for A is negative 3, negative 1, 0, 2, and 4. Not negative 3 to 4, right? It's just those specific 5 numbers. For B, you can't divide by a negative, so the domain is x cannot equal negative 5. That's the number that would make the denominator 0. For the volume of a sphere, for C, is there any number that we could plug in for R that would make this go bad? No, we can divide by 0. Or I'm sorry, we can divide by whatever we want. There's no square roots, no dividing by 0. So in this case, the domain is the set of all real numbers. And last one here for D. We know that 4 minus 3x has to be greater than or equal to 0. All right? So 4 is greater than or equal to 3x, divided by 3, and we've got 4/3 x. So the domain x has got to be less than or equal to 4/3. Otherwise, we're taking the square root of a negative number, and that's not going to work out. See if you can do this yourself. For example, our exercise 73. All right, let's take a look at the dimensions of a container. You work in the marketing department of a soft drink company and are experimenting with a new can for iced tea that's slightly narrower and taller than a standard can. For your experiment, the ratio of the height to the radius is 4. So height over radius equals 4. All right. Write the volume of the can as a function of the radius r. 1 second. All right, so the formula for the volume of a can is volume equals pi r squared h. For problem A, we want to write this as a function of r, v as a function of r, which means we can only have r's in our final answer. All right, so we have pi, that's all right because it's just a number. R squared, that's okay. We need to get rid of the h here. So we need to solve h in terms of r over here. So we're going to times both sides by r. So now I know h equals 4r. So now instead of writing h, I'm going to write 4r. And from here I'm just going to simplify. V as a function of r equals 4. I'm going to bring it just to the front. Pi r cubed, r times r squared. And that's your answer. For part B, v as a function of h, we've got pi equals pi r squared h. We've got to substitute the r out of here, right? So this is pi. Instead of r, we can say h divided by 4 equals r. H over 4 squared h. And so to finish this, we've got pi over 4 squared is 16 h cubed. H squared and another h. All right, go ahead and try example 87. All right, so path of a baseball. We have a baseball hit at a point 3 feet above the ground with a velocity of 100 feet per second at an angle of 45 degrees, and they give us this function. Will a baseball clear a 10-foot fence located 300 feet from home plate? Well, let's find out. In this problem, negative 0.0032x, all right, is how far away from home plate we are. All right, right? X is the distance from home plate, and so we put a 300 in here, squared, plus 300, plus 3, and if we go ahead and solve this, I have to go to the textbook, I don't have my calculator on me. The answer here is 15, right? And that definitely will clear a 10-foot fence. We could put this in our graphing calculator and trace it and go to where 300 is and see what the y value is. It's small here, but you can see it. X is 300, y is 15. So 2 different ways to do this. All right, you're up on exercise 93. Home stretch here, example 10. All right, on this one, we're going to put this into our graphing calculator, right? And solve this for all of the different functions. Go ahead and pause on this one. Make sure to remind me in class that we need to go over example 10 together, because I want to make sure everybody can do this piecewise functioning in their calculator. All right? If you want to take a shot at exercise 95, go for it. All right? You can do this without the graphing calculator, but remember, we're going to go over this one together in class. All right, last thing here is the difference quotient. We have a formula here. It's f of x plus h minus f of x over h. You need to memorize this formula. This is called the difference quotient. It will be on your test. It'll be on the final. You need to know it. All right? So let's figure out how this works. They're going to give you a formula. You need to plug it in. F of x plus h. That's our first portion right here. All right, we're going to plug in x plus h everywhere we see x. So x plus h squared minus 4 x plus h plus 7. Then, so that's our first piece. We put big parentheses around it. Minus f of x. Actually, let me do this in green so we can see it. Okay? That's just our original equation. X squared minus 4x plus 7. All over h. I'm going to leave that h out until the end. Just for space, it works out a little better if we wait to clean it up. So let's clean this all up. This is x squared plus 2xh plus h squared minus 4x minus 4h plus 7 minus x squared plus 4x minus 7. Let's do some canceling. 4x cancels. 7 cancels. Anything else cancels? X squareds cancel. And if we rewrite this, we have h squared plus 2xh minus 4h. And now I'm going to bring this back in. We haven't had this yet, but it's all over h. Let's go ahead and cancel where we can. I'm going to pull an h out on the top. So I'm left with h plus 2x minus 4 all over h. These h's cancel. And our difference quotient is going to be h plus 2x minus 4. All right? And that is our difference quotient. All right? This is tricky. Try exercise 103. These are hard ones. We will definitely go over this in class as well. Good luck with this. Any questions, please come and see me. The last thing on here, this is at the end of your chapter, a nice little summary of what everything we've talked about. Okay, make sure that these things are in your notes here, okay, or at least you know what's going on when we talk about them. All right, we'll see you in class.